Okay, so we're leading up to how do we solve a differential equation using the power series or series in general. And this is one step further as to get there. Okay, so unfortunately, well, some of these we could do already, and some of these we can't do the methods we've done so far. So again, like I said, life isn't perfect. Sometimes these are the methods we have already won't actually work, which is really, really bad. So the alternative is using series. More importantly, just the power series we're going to be using with itself. And that's already enough because a lot of these are very, very painful to solve for these kind of scenarios. So what this is all about is just a review of the power series, radius conversions, and anything, things in a nutshell when it comes to series in general. Okay. So first off, we go to what's the actual power series itself. So a power series at the point x naught is the expression this. Okay. Where x is a variable, therefore the a sub n's are constants. So again, if we go to conversion divergence, therefore if we limit, it converges to a value of L, right? So again, this is just a brief review of what power series represents, but what we care about is we're going to be using the power series to somehow simplify some stuff. Okay. So since we're talking about power series, we can see if it's, do we actually have a solution or not, right? Depends if this is convergence or diverge. That's the key thing. So we could actually check, does this actually series converge? Basically, that means there is actual solution, or if it diverges, meaning there's no solution or possible to do so. It's, we're just completely, unfortunately, wasting our time. Okay. So again, just a brief understanding of what it means to be a convergence. We're going to be doing absolute convergence, which makes it easier. So we're not going to do the basic one. We're going to go straight to absolute convergence using the power series. So what that means is, because it's absolute, we're going to have a radiance of convergence. Okay. So for each power series, there's a number, we'll call it a rho. Rho that's greater than 0, that's less than infinity, so it actually is an actual number. Call the radius of convergence, well, technically it could be infinity too. Radius convergence of the power series such that it converges absolutely, basically. When you subtract this difference, it is less than this rho value, or rho value there. And diverges if the absolute value of this difference is greater than that particular value, right? It means it always unbounded itself. Okay. If the series converges for all values of x, then rho is infinity. So basically what's happening here is if it actually converges, rho is actually infinity itself. It just keeps getting growing and growing and growing and growing. That's what ends up being it. Now this is also a key thing. The series converges only at x naught, then p is a 0. So if it only converges at the actual point, then we have the other extreme of being 0 itself. So basically it's going to be one or the other. That's pretty much what's happening. Okay. So if you just go back to interval notation, what this is saying about this, divergence and convergence stuff is, if I have an x naught, so I have a series centered at this point here. So therefore, if I add rho to this and I subtract rho to this, I actually have an interval. Right? It could be a really big interval, but it's some interval here. So as long as I have an interval, this converges absolutely. Anything outside the realm, that means it diverges. That's pretty much what it represents when it comes to radiance convergence, or absolute radiance of convergence itself. Okay. So the question now becomes, how do we test for convergence and divergence itself? And that's an extra step here. So just using the ratio test is probably the fastest and simplest way to do any series test. It's the one that everybody loves the most because it's pretty straightforward. Plus we want the absolute, so we kind of have to use this one. So it's a series divided by its series plus 1, and if the limit goes to infinity, it gives you an L, therefore it converges, right? It's pretty straightforward kind of process itself. Again, this represents this definition of basically our power series converges to L, which means if this is true, our rho is the L value itself. Again, both extremes are possible. Okay. What we really care about mostly is this process here is, well, we've seen a little bit in Cal 1 is the derivatives of a series. And believe it or not, you can actually take derivatives of series. You can take integrals of series. You'll see that in a little bit as well. So if we have a power series and has a positive radius convergence, basically this is true, um, then we could take the derivative of the power series, and at that point it's just the same thing as just the derivative of any portion. It is a product or chain rule, derivative of the inside times the derivative of the outside, so you just bring it to the front, to the power, and derivative of the inside is always just going to be 1 because it is x minus x naught, which is always a value. Derivative of x is just 1, so technically just 1 out here. So it really is a chain rule, but you could just use the power rule itself to cheat sheet of it. Okay, and same thing applies for integration, right? So this is the integral, so let u equal the inner, so therefore it's just u to the n power. So what's the integral of u to the n? U to the n plus 1 over n plus 1. So that kind of makes sense, right, when it comes to these portions. Again, the nice thing is this n starts at 1 because the derivative of constant is just 0, so the last term just goes away. That's why we start with 1, and this one still starts with 0, it's respectively. Okay. And again, these are its radius of convergence themselves, right? They're both the same because the convergence doesn't matter if it's, this is going to be infinity, but if it just gets smaller, it's still infinity, just going rapidly. Okay. So much of this part is going to be is, well, how can we just define power series and get comfortable with power series? That way when we start solving for differential equations, it's not as difficult to deal with all into one nutshell itself. Okay. So most of the time we're going to be dealing with is how do we use existing, just like Laplace transformations, how do we use existing power series to solve for differential equations? Okay, so all we want to do now is manipulate. So for example, knowing that this is the power series for, this is the power series for this one, how do we manipulate these three to make it look like this, so we can use this as a power series for each one of these? Okay, so we'll just start from here. So we know this is 1 over 1 minus x. This is very similar to that, right? But it just plus x squared. So if I can rewrite this and say, I'm going to say let x equal negative x squared, this process. So if I just recalculate this part, make it kind of look like this. So it'll be 1 over 1 minus negative x squared. So now it looks very similar, and all I'm really going to do now is plug this in for x. So these are going to be the same values themselves, right? It's x, x. But if this changes, therefore this is going to have to change here. But we're going to do a little bit better than that. So let's just look at this process more closely. Okay. So technically, this is negative 1 times x squared, right? Because that negative is on the outside. So now if I raise this to the nth power, right? So right now we just have the sum of this happening. But if I want to simplify this a little bit more, so I'm just going to raise this to the nth power. And according to our rules of exponents, is just distributive property, I get negative 1 to the n times x raised to the 2n power. So really, our power series simplifies to this. And there we go. So now let's try one of these theorems to help us out. Okay. So unlike here, this one goes here. This one's squared in the bottom. So that's pretty interesting. Now, you may think, well, I just have to square everything. Well, kind of tricky, that portion, because then it basically gets the same process here. But if you notice, let's go here to here. If I take the derivative of this, I get this. In other words, 1 over 1 minus x squared is equal to the derivative of this. Okay, so if this is the derivative, therefore I could follow this process And all I'm going to do is just take the derivative of each individual term and then just call it a day. Right? So how we're going to do that, and you can see how this is going to lay out process, is I'm just going to write this in series notation. So I'm just going to plug in the numbers. So for example, if I plug in 0, so x to the 0 is just 1, plus x to the first, plus x squared, plus x to the third, and it keeps going, right, all the way to x to the n. So if I take the derivative now, well, this goes to 0, plus 1, 2x, 3x, n, x to the n minus 1. Okay, so therefore, this sum, or this power series, is equal to n times n to the n minus 1 power, which is exactly what we had here, right? Like that. So this is just an understanding of how this works, but if you just want to use a theorem, you could just straight take the derivative, and exactly we're done there, which is pretty nice. Which gives us every single term. If n equals 0, this is times 0, so it gives you the first point, which is check. And if you really want, this is the same thing as just going to 1. So that's why in the definition, it just gets rid of the first term because you're going to get 0. So that's why we start at 1 here, not just 0. But you could technically do it, but they equal each other since you're technically just adding 0 to this term. Okay. So now let's go one that's not so fun to deal with, and there's a lot of trig involved. Tan inverse of x. Okay. So this one uses a little bit of a finesse. Okay. Because tan inverse of x, if you're wondering, right, to follow this process, if you see in these examples, this is a derivative, so this might be an integral to follow this process here. So that's actually true because the integral, or what the integral of something gives you tan inverse, is actually 1 over 1 plus x squared. Okay. So if this is the integral, so therefore I'm going to have to take the derivative of both sides, or just integrate when it comes to it. All right, so if that's the case, so if I take the derivative of tan inverse of x, this is in the beginning 1 over 1 plus x squared, right? Okay, so what I'm going to do now is just, again, like we did last time, just plug in numbers, or plug in this power series, and just take the integral at that point. Okay. All right, so if that goes by, but the problem is we can't do this one. We actually already know the power series to this. We did it earlier, which is right here. So if I just do what I did here, just do each individual term. So if n is equal to 0, oh, sorry, this is in there. If n equals 0, we get 1. If n is equal to 1, we get x squared. This is a negative, so negative x squared. If n is equal to 2, we get positive x to the fourth. And as you can tell, it just goes plus or minus all the even powers. So now if I take the integral of this entire thing, I get x minus x to the third over 3 plus x to the fifth over 5. And notice I actually get the odd powers now. Okay. So this power series, again, goes plus or minus, so it's about the same thing, negative 1 to the n power. But now we just got to figure out the odd powers on the top, and then it's going to be the same thing on the bottom. So to get every single odd power is always going to be 2n plus 1, always guarantees you an odd number. And since they're the same, top and bottom, it could just be x to the same value itself. So there is our power series of that. Okay. So again, all we want to do is manipulate it in such a way, and you'll see how it is. Again, just a review of power series manipulations itself. And then the last thing is how we follow, or how do we adjust the indexes of series. Okay. So for example, if I don't want to start with 2, and I want to start with another index, or I want to change the terms themselves. Okay. So just again, just a review of shifting indexes in some situations is, when it comes to these two now, I want to express the series using a generic x to the k, meaning there's no power here, just like an arbitrary k or n power itself. And same thing here, and this is supposed to be an n actually. We'll get there. Now, again, usually how this is going to go by is we just set the equal to what we want. So I want this to be k, not n minus 2 anymore. So I set equal to that. So I want k is going to be to n minus 2. And I just work my way backwards. So therefore, to manipulate this portion, so n must be k plus 2. Okay. So now what I'm going to do is, everywhere I see an n, I'm going to rewrite it with a k plus 2 term. So this is not good notation, but hopefully you understand what I'm about to do. So it's going to be k plus 2 equals 2. K plus 2 times, and in parentheses, k plus 2 minus 1, a to the k plus 2, x raised to the k plus 2 minus 2. So now, if I subtract 2 to both sides here, we get the index of 0. This stays the same. Just putting those together. And now these cancel, and I get exactly what I want. So I have a term of x to the k power. So here is our transition, or shifting of indexes. Okay, same process. So we want everything in terms of k, so I'll just follow the same process we did earlier. So solving for n will be k minus 3 this time. And if I follow the exact same steps we did above, just replace everywhere I see n with this now. I'm going to have k minus 3 equals 0, k minus 3 to the second power, and just again, replug in everything. So here, bringing it to this side now gives you, we're starting with the third term. And again, we get where we desire to be. So there we go. Now again, all we're trying to do is just a little review of power series, converting, stuff like that. I do have just a little bit of a cheat sheet for you guys we're going to be using in next couple sections, and how do we go from one to the other, and signifying which one we're going to be using, and vice versa. Just like Laplace transformation is, okay, here's the power series for this. Well, what does it look like going backwards and forwards? Okay. Before we get there, there is one special definition we're going to use going forward. It's something called an analytic function. Okay. So analytic function f is said to be analytic at x naught, so at a single point x naught, if in an open interval around x naught, so here's x to the point, open interval, right? This function is the sum of the power series, so that has a positive radius of convergence. So it looks, what in the world does really mean? We'll get in more detail later on, but it's just a nice little definition to start with going forward, because we're going to figure out, okay, what does it mean to be analytic, and what does it mean to an actual series itself for differential equations.